So this lesson is looking at some past exam paper questions on P12 wave properties and P13 electromagnetic waves. So question number 1 says you've got a figure there which looks like the ripple tank, shows the equipment a teacher used to determine the speed of a water wave. The equipment includes the ripple tank filled with water, a wooden bar that creates ripples on the surface of the water, so the dipper, a light source, the lamp, which causes a shadow of the ripples on the screen below. And question A says, describe how equipment in figure 1 can be used to measure the wavelength and the frequency and then the speed of the water wave. So let's first of all, this is a 6-mark question, so let's see if we can do the first bit, which is work out the frequency. So what we need to find the frequency of the water wave, you can use a stopwatch. So what you do is you count the number of waves passing a point in a fixed time period. You decide on the point and you choose a time, let's say 10 seconds. Okay, and you count the number of waves that pass using the stopwatch in 10 seconds. Then you divide the time, which is 10 seconds for example, by however many waves have passed that point to determine the time for one wave, which is of course the time period t. And once you've got the time period capital T, then you know the equation F is equal to 1 over T, and that will give you the frequency. Okay, so that's the first bit. Second bit is to work out the wavelength. So to find the wavelength lambda, use camera is probably easier. Take a photograph of the screen, then use a meter ruler. Make sure that the meter ruler is already in line when you take the photograph of the screen as well, and measure the distance between two wavefronts, okay, that are a little bit far apart. Count the number of waves between the wavefronts, okay, maybe 10, then divide the distance that you've measured by the number of waves, and that gives you the value of lambda, the wavelength, because these shadows that are created, or these wavefronts that are created, will be perhaps the crest of a wave, so crest to crest. Okay, so that gives you the wavelength. Now, once you've got the wavelength and you've got the frequency, you can use you can take these readings again, maybe 2 more times. So take 2 more readings of the frequency and then work out the mean value of the frequency. Do the same thing for the wavelength, record some more wavelengths by taking some measurements of distance between 2 wavefronts and then dividing by the number of waves in between the 2 wavefronts. Get a mean value for that, and then because you've got the frequency and the wavelength, you can use the wave equation v is equal to f lambda to determine the wave speed. Okay. So the next part of this question, part B, says the teacher then put a plastic duck in the ripple tank as shown in the figure 2. The plastic duck moved up and down as the waves in the water passed by. There you can see the movement of the duck up and down. B, how does the movement of the plastic duck in figure 2 demonstrate that water waves are transverse? Well, we must remember the definition of transverse waves. It means that the direction of oscillation or vibrations of the object or particle is perpendicular to the direction of the waves, the movement of the waves or the energy transfer. So we can say the duck moves perpendicular to the direction of wave travel. Okay. So part 1C, the teacher now measured the maximum height and the minimum height of the plastic duck above the screen as the wave passed. The teacher repeated his measurements. The table shows the teacher's measurements. So you've got the maximum height in millimeters has been recorded 3 times, and then you've got the minimum height in millimeters, which has also been recorded 3 times. You've got to calculate the mean amplitude of the water wave. So the first step that you need to take is you need to work out the mean maximum height, and you do that by adding the 3 values 509, 513 and 511. Divide it by 3 because there are 3 maximum height values there, and you get 511. Do the same for the mean minimum height. Add all the 3 numbers together, divide them by 3, which is how many numbers there are for the minimum height, and you get 500. If you do 511 take away 500, you get a value of 11. That's the difference between the 2 mean values of the maximum and the minimum height. And as there are 2 values, if you divide those by 2, you get the mean amplitude of the wave as 5.5 millimeters. Okay. Question number 2 says a note was played on an electric keyboard. The frequency of the note was 440 Hertz. Part A1. What does a frequency of 440 Hertz mean? So we just got to define what frequency is basically by using 440. So that means it's 440 waves, or in this case sound waves we're talking about, every second. So we can say it's 440 sound waves or oscillations or vibrations produced in 1 second. Okay. Part 2 says the sound waves produced by the keyboard travel at a speed of 340 meters per second. Can you calculate the wavelength of the note? Give your answer to 3 significant figures. So what we do is we use our wave equation. V, the wave speed, is equal to the frequency times the wavelength. We can use our formula triangle or rearrange to make wavelength the subject of the equation. So wavelength lambda is equal to wave speed divided by frequency, which is 340 divided by 440, and we've got to do this to 3 significant figures, so it's 0.773 meters. Okay. Question 2b says figure 1 shows a microphone connected to the CRO, cathode ray oscilloscope, being used to detect the note produced by the keyboard. So you've got, there's a setup, then you've got figure 2, which shows the trace on the cathode ray oscilloscope produced by the sound wave. And in figure 3, we'll see on the next slide, we can compare the 2 traces that are produced. So here we have the second note of a different wavelength as played on the keyboard. Figure 3 this time shows the trace produced by the sound wave of the second note on the CRO. We've got to compare the 2 from the 2 traces, so figure 2 and figure 3, and the settings of the CRO were unchanged. What 2 conclusions should be made about the second sound wave produced by the keyboard compared with the first? The second one, we can see that the amplitude is bigger. Because of that, we can say that the sound is louder. So the conclusion will be that the sound is louder because the amplitude of the second wave is larger, as we can see on this trace. Okay, and the amplitude here is about 1 square and a bit more. Okay. Now, the second conclusion that we can also draw is that the second trace in figure 3 has a higher pitch or a higher frequency because the number of waves are greater than in figure 2. So there's more waves here we can see compared to the previous figure 2 trace. So question number 3 says the sun emits all types of EM waves. Figure 1 shows the electromagnetic spectrum. There they are. Remember that radio waves have the longest wavelength and therefore the smallest frequency, whereas the gamma rays have the smallest wavelength and the largest frequency, or the highest frequency. Okay, then we've got to complete the sentences. In a vacuum, all electromagnetic waves travel at the same, velocity. Okay, that remains unchanged. Gamma waves have the greatest, as I've just said, they have the greatest or the highest frequency, and radio waves have the greatest wavelength, and so we put the wavelength there. Okay. Question 3b is still on the electromagnetic waves topic. Explain why it is important that the Earth's atmosphere absorbs gamma rays emitted by the sun. Well, we know that gamma rays are harmful. They are ionizing radiation, so we can say that so that people are not exposed to as much gamma radiation, because gamma radiation is ionizing, which means that it can knock off electrons out of atoms, so it can lead to what we know as cell mutation, which can increase the risk of cancer and cause damage to human tissue. Okay? Some microwaves are not absorbed by the Earth's atmosphere. Why is this useful? Well, microwaves are able to be used in satellite communications if they are not absorbed by the watery atmosphere. So here we have a graph where it's looking at some ultraviolet radiation that's coming in from the sun, which passes through the atmosphere and reaches the surface of the Earth. The amount of UV radiation that reaches the surface of the Earth can be measured on a scale called the UV index. So the UV index is plotted on the y-axis and the months of the year on the x-axis, and figure 2 shows the average midday UV index in the UK over the course of a year, month by month. So we are going to use this graph to compare some stuff. So part D is relating to the slide on the previous slide of the graph there. Why is exposure to UV radiation harmful to humans? We should know that it is harmful because UV radiation can cause skin cancer. It can also lead to premature aging, in some cases cause damage to the eyes, including blindness, and can cause you to burn your skin as well. Okay. Compare the risk from UV radiation at different times of year in the UK using the graph from the previous slide, figure 2. We can say that the risk from UV radiation is highest in July with the highest UV index value of 9, and the risk from UV radiation is lowest in December with the lowest UV index value of 0.7. So there we have compared the two highest and lowest risks of UV radiation by month. So question 4 on electromagnetic waves. There are different types of electromagnetic wave. Which type of electromagnetic wave has the shortest wavelength? The shortest wavelength is about 10 to the power minus 15 Hertz, and that is the one with the highest frequency, and that's the gamma rays. Okay, and now it says part B, a new technology has been developed to charge small electrical devices from the radio waves in the air around us. Explain how radio waves could charge a small electrical device. So we could say the small electrical device absorbs or receives the radio waves, which creates an alternating current of the same frequency as the radio waves. Part C is for us to complete the figure to show the wave fronts as they pass out into the air. So we've got a glass block. We know that it's optically denser than the air. So we can see that the wave fronts, what happens is when light passes through or waves pass through a denser material, they bend towards the normal. The wave fronts get closer together. Okay, but when it now has to emerge back out into the air, we should find that the wave will, or the ray at least, will bend away from the normal. The wave fronts will become further apart, and because it's still air, it should be refracted parallel to the incident wavefront and ray diagram there. Okay, so we should have something along those lines there, sort of parallel to the incident ray at the other end of the air glass boundary. Okay. So the next question is to part D, explain why there is refraction at the boundary between air and glass. We can say that the wavefront slows down in glass. One edge of the wavefront enters the glass before the other, as we can see from the previous diagram. One edge of the wavefront slows down before the other, so the wave changes direction. So that's 3 marks there. And the next part is a calculation question. Must be using the wave equation. The period of a wave in a ripple tank was measured. The period is given for this wave as 420 milliseconds, or 0.420 seconds, because we divide 420 by 1,000 because it's milli. The speed of the wave was 0.6 meters per second. Calculate the wavelength of the wave. So before we use the wave equation, we've got to use the equation linking frequency and time period. So F is equal to 1 over T, which gives us 1 over 420 milliseconds. Converting the milliseconds to seconds gives us 0.420, and we get our value for frequency of 2.38 Hertz. Now we've got the frequency and we've got the wave speed. We can use our wave equation, which is V is equal to F lambda, to calculate the wavelength of this particular wave in the ripple tank. So we rearrange that equation to make the wavelength the subject of the equation. So the wavelength lambda is equal to V over F, which is equal to 0.60 divided by 2.38, which gives us 0.25 meters. Okay, and that's the end of that revision topic on past papers covering wave properties and electromagnetic waves.